Assalamualaikum and hi for those watching this video. In this video, my friend and I want to explain about our video assignment for MAT183, which is Techniques of Differentiation. So, this is my group members. I'm Muhammad Haras Hazik bin Hairuddin. Second is Zurizat bin Zulrahman. And last but not least is Muhammad Aidil bin Amir Muhammad. Without wasting time, I will explain what differentiation means. Differentiation is a process in calculus used to find the rate at which one quantity changes with respect to another. It measures the slope or gradient of a function at any point, which tells how a function is changing at that point. In simpler terms, differentiation gives the derivative of a function. So, let's move to the next slide. There are many techniques of differentiation that we will learn in this topic. First is power rule, second is constant rule, third is constant multiple rule, four is product rule, five is quotient rule, six is chain rule, and last but not least is sum and difference rule.
Hi everyone, my name is Muhammad Aidil. In this presentation, I walk you through the solving two calculus problems involving the derivative using the product rule and the quotient rule. Alright, let's start with the first function. Y equals e to the power of 2x times the quantity x squared plus 5x all raised to the third power. Since we're multiplying two expressions, we're going to use the product rule. I call the first part u, which is e to the 2x, and the second part is v, which is x squared plus 5x all cubed. The derivative of u is straightforward, it's 2 times e to the 2x. For v, we use the chain rule, we bring down the 3, keep it the inside part x squared plus 5x, now square, and multiply it by the derivative of the inside, which is 2x plus 5. Now applying the product rule, we multiply u by v prime plus vu times u prime. That gave us this expression, 2e to the 2x times the quantity x squared plus 5x cubed plus e to the 2x times 3 times the quantity x squared plus 5x squared times 2x plus 5. Both terms with a common factor, so we can factor out e to the 2x and x squared plus 5x squared. When we factor those out, we get the final simplified from e to the 2x times the quantity x squared plus 5x squared, all multiplied by the quantity 2 times x squared plus 5x plus 3 times the quantity 2x plus 5. For the part B, this time the function is y equals the natural log of x plus 1 divided by sine of 4 times the natural of x. Since this is a division, we must use the quotient rule. We call the top part u, which is the natural log of x plus 1, and the bottom part v, which is sine of 4 natural log x. The derivative of u is just 1 over x plus 1. For v, we use the chain rule again, the derivative of sine equals sine, and the inside function is 4 natural log x, so the result is 4x times cosine of 4 natural log x all over x. Now we apply the quotient rule. Take v times u primes minus u times v prime and divide all of that by v squared. So we get sine of 4 log x times 1 over x plus 1 minus natural log of x plus 1 times 4 cosines of 4 log x over x. And all of that is divided by sine square of 4 log x. And that's it. We use the product rule in part A and the quotient rule in part B, breaking it down step by step, but really helps, especially when chain rule is involved. Thank you.
We are given the following equation: e to the power of 3x minus ln x plus y equal to sec 2y plus 5x. Our objective is to find dy dx using implicate differentiation. Since y is a function of x, We begin by differentiating both sides of the equation with respect to x. For the left-hand side, the derivative of e to the power of 3x is 3e to the power of 3x. The derivative of ln x plus y is 1 over x plus y, derivative 1 plus dy dx, using the chain rule. For the right-hand side, the derivative of sec to y is 2 sec to y tan to y dy dx, again using the chain rule. Derivative of 5x is simply 5. Step 2. Combine all the derivative. Putting everything together, the differentiate form of the equation becomes 3e to the power of 3x minus 1 plus dy dx over x plus y equal to 2 sec to y tan to y dy dx plus 5. Step 3. Rearranging the terms. We now collect all the terms with dy dx on one side and the rest on the other side. After simplifying, we get dy dx. After simplifying, we get dy dx multiply 2 over e to the power of 3x plus 1 over x plus y minus 2 sec to y tan to y equal to 5 plus 6y over e to the power of 3x plus 1 over x plus y. Step 4. Solve for dy dx. Finally, we isolate dy dx by dividing both sides. Dy dx equal to 5 plus 6y over e to the power of 3x plus 1 over x plus y over 2 over e to the power of 3x plus 1 over x plus y minus 2 sec to y tan to y. And that's the final answer. By applying implicit differentiation carefully and using the chain rule, we successfully found the derivative dy dx.
Next, we go to the question 4, which is use linear approximation to estimate the value of the fourth root of 16.37 plus 1 over the square root of 16.37, correct to two decimal places. First, we need to find the x, which is 16.37, x naught, which is 16, and delta x is 0.37. The second thing we need to do is to create fx by substituting 16.37 from the question into x. The third thing is to find the f prime x, where we have to convert the fourth root of x and 1 over the square root of x to fractions. Then, we convert again using the techniques of differentiation. Next, we need to find for x naught by change the value of x to 16 from equation fx, and we get 9 over 4 for the answer. Next, we want to find the f prime for x naught. We take the result of the calculation of f prime x just now and change the value of x with 16. The answer that we will get is 3 over 128. Last but not least, we combine all the answers in the formula of linear approximation and differentials, and the final answer is 2.26. In conclusion, the techniques of differentiation are essential tools in calculus that allow us to analyze and understand the behavior of function. From basic rules like the power, product, quotient, and chain rules to advanced methods involving implicit and logarithmic differentiation, Each technique serves a specific purpose in solving complex problems. Mastery of this method not only facilitate accurate computation of derivative, but also enable deeper insight into rates of change, optimization, and motion, making them vital in both pure and applied mathematics. That's all from us. Thank you.